Welcome to Module 2, Part 3. In this section, we will be discussing about the oscillators. As you all know, an oscillator is a circuit that produces a periodic waveform on its output with only the DC signal or the DC supply as the input. It is an electronic circuit that generates the output signal without the necessary input signal. They are used as signal sources in all sorts of applications. Different types of oscillators produce various types of outputs like the sine wave, square wave, triangular wave, and sawtooth wave. We have seen triple pipe timer, Smith trigger, all are different types of oscillators. Sinusoidal oscillator operation is based on the principle of positive feedback, where a portion of the output signal is fed back to the input in the way that it causes to reinforce itself and thus sustain a continuous output signal. Oscillators are widely used in communication systems, in computers to generate a required frequency and timing signals. Let us discuss different types of oscillators one by one. So this is the diagram of the RC phase shift oscillator. Here we have an op-amp with the input fed to the inverting terminal. So this acts as an inverting amplifier which provides a phase shift of 180 degree. Then we have the RC network combination over here. Three RC combinations are connected back to back. Each RC combination will provide a phase shift of 60 degree. So three combinations or the three RC networks will provide a phase shift of 180 degree. So the total phase shift is 0 degree, or this plus this. Total phase shift is 0 degree or 360 degree. So this is one of the condition for sustained oscillation. As you all know, the Parkinson's criteria for oscillation, there are two conditions for oscillation, for the sustained oscillation. The first condition is the phase shift around the loop. So this is the loop. The phase shift around the loop should be 0 degree or 360 degree. So with this, the first condition is met, that is the phase shift around the loop is 360 degree. Second condition is the closed loop gain A around the loop is equal to A V, the gain of the op-amp, into the B, or the attenuation of the feedback network. This is a feedback network over here. This is a feedback network. So the attenuation of this B over here and then AV of this should be equal to unity. So ACL, the closed loop gain of the entire circuit should be equal to unity. So the attenuation in this particular circuit B is equal to 1 by 29. So in this case the gain AV of the op-amp should be 29 to make the closed loop gain equal to 1. So if we set the gain of the op-amp as 29, then the second condition of the oscillation will be met and we will get a sustained oscillation at the output, a sine wave at the output. Now you all know how to make this AV29. This is a non-inverting amplifier. You can see input is applied to the non-inverting terminal. So the gain AV is equal to minus RF by R1. You all know this gain equation, voltage gain equation of the non-inverting amplifier. By selecting a value of R1, we can select a value of R1 as 10K. In this example, it is selected 12K. AV should be 29, so that there will be sustained oscillation. 29 into 1 by 29 will be equal to 1. So AV should be 29. R1 can be selected as 10K. With this we can calculate RF. As a result, the gain AV will be 29 and totally the closed loop gain ACL will be 1. The frequency of oscillation F in this particular circuit is 1 upon 2 pi square root of 6 RC. This R is these three R values. We have already selected R1 and we have calculated RF. So these three RF over here in the feedback circuit is this R, and this C over here is this particular C. So the frequency of oscillation is 1 upon 2 pi square root of 6 RC. Next is the crystal oscillator. This is the circuit diagram of crystal oscillator. Crystal oscillator is a tuned oscillator which uses quartz crystal in the tank circuit. This is the quartz crystal. Quartz is one of the crystalline substance found in nature that exhibits the property of piezoelectric effect. So you might be knowing about the piezoelectric effect. Piezoelectric effect is the ability of certain material to generate an electric charge in response to the applied mechanical stress. Voltage is developed at the frequency of mechanical vibration. The crystal oscillator is preferred when high frequency stability is required. The crystal oscillator are used in radio transmitters, TV transmitters, crystal clock in microprocessors, and other electronic applications. Crystal oscillator usually generate a very high frequency, around 2 megahertz. We have already done one experiment in the lab and it generates a pure sine wave of very high frequency. This is the circuit symbol over here, the circuit symbol, the equivalent circuit of the piezoelectric crystal. The crystal equivalent circuit, the diagram B, is series parallel RLC circuit and can operate either in series resonance or parallel resonance. At series resonance frequency, the inductive reactance is cancelled by the reactance of Cs. The series resonant at Ws is given by this particular equation. It is 1 divided by square root of L Cs. Series Cs stands for series capacitance. Parallel resonance occurs when the inductive reactance and the reactance of Cp are equal. The parallel resonance at Wp is given by this particular equation, 1 divided by square root of L into Cs Cp divided by Cs plus Cp. Cs is series capacitance, Cp is parallel capacitance. The parallel resonant frequency is higher than series resonant frequency, that is omega p is higher than omega s. However, since Cp is far greater than Cs, the parallel capacitance value is far greater than Cs, then the two resonant frequency are very close, that is omega p is almost equal to omega s. In the previous slide we have seen the RC phase shift oscillator. Although the RC feedback oscillator is generally used for frequencies to generate the frequencies up to 1 megahertz, the LC feedback elements are normally used in oscillators that require higher frequency of oscillation. Because of the frequency limitations of most op-amps, discrete transistors such as BJT or FET are often used as the gain element in LC oscillators. There are different types of LC oscillators like the Colpitts oscillator, Hartley's oscillator, Clap oscillator, Armstrong oscillators. But we'll be discussing only two types of oscillators. One is the Colpitts oscillator and the second one is the Hartley's oscillator. This is the diagram of the Colpitts oscillator. Here we have the feedback circuit. This is the feedback circuit with the two capacitors and one inductor, and this part is the amplifier stage. We have done this amplifier, the BJT voltage amplifier, as a part of an experiment, experiment number 1. So this is the amplifier stage and this is the feedback stage over here. This is named after the scientist who invented this oscillator, Colpitts. This type of oscillator uses LC circuit in the feedback loop to provide the necessary phase shift, and it acts as a resonant filter that passes the desired frequency of oscillation. The frequency of oscillation in this particular circuit is F equals to 1 upon 2 pi square root of L C total. C total is L and C are in the tank circuit, C total is these two capacitors C3 and C4. So these two capacitors in series, they will be C3 into C4 divided by C3 plus C4. So this is the total capacitance, and the frequency of oscillation is 1 upon 2 pi square root of L into C total. Next is this is the circuit diagram of the Hartley's oscillator. Again, it is named after the inventor Hartley. Here the feedback circuit consists of two inductors and one capacitor. This oscillator is exactly similar to the Colpitt's oscillator, except that the tank circuit consists of two inductors and one capacitor. This is the BJT voltage amplifier stage, which amplifies the signals fed from this feedback circuit. The frequency of oscillation F is equal to 1 upon 2 pi square root of L total into C. This L total and C are from the tank circuit. This is the tank circuit. So L total over here, the series combination of the two inductors L1 plus L2. So these are the different oscillators. One is the RC phase shift oscillator, then the crystal oscillator, then the LC oscillator, one is Colpitt's oscillator, and second one is the Hartley's oscillator. So this finishes your module 2. Thank you.